and we shall move to the next contribution, which is about PDF VegasFlow from Juan.
Okay.
Share your slides.
Let me share my screen. Okay. Are you seeing my screen now?
Yes.
Perfect. So this is a good follow-up to the previous talk. I have to say I was not able to attend properly the beginning of the session because I had some teaching, so maybe there will be some redundant slides. So sorry about that. Okay. So basically, so at the beginning, I will basically motivate why we are doing this. Most of what has been discussed in the previous talk also applies here. And then I will explain what they are exactly and show some specific examples. So first of all, coming to the integral that we want to solve, or the equation that we want to compute, is the famous cross-section integral that I'm sure many of you have already seen, where there are three main components. So the matrix element, which basically contain the physics of the process. Then you would have your jet function and the phase space, which defines the region of integration, and then the parton evolution functions, parton distribution functions, sorry, that define the initial state. From a technical point of view, and showing a diagram very similar to what has been shown in the previous talk, you need a series of ingredients to produce a Monte Carlo generator, right? You need some integrator, and then you need to generate the phase space and the cuts to define the space of integration, a matrix element for the process, the initial stage, and then some histogramming and analysis. And since this is usually done using Monte Carlo methods are one of the most parallelizable things I can think of, because each event is completely independent of every other event to first approximation. So one could say, okay, I have this integral, I just apply parallelization without thinking about anything else, and one would already get some kind of speed up without even thinking about doing it in a particular way or optimized way. And then one could ask, why is GPU computing not more widespread in our community? So I'm coming from fixed order, higher order calculations, and so this is my point of view, coming from that background. But one of the reasons, and maybe the main reason, is we are in a situation of diminishing returns, right? Because one have this huge Fortran 77 code base. If you are lucky, maybe Fortran 19. And then as a student, you are tasked with writing a new code for some new process, some exotic process, some higher order calculation. Then it's much easier, after you spend a few years writing the matrix elements, to expand the code that you already have, which means that for the next student, it becomes even more difficult because the code has grown. This brings a lack of expertise in the field, because everyone is used to do these things on CPU, doing these things in Fortran. So at the same time, for going to a GPU, you would need a different language. So again, we are in a situation of diminishing returns. And then there is a situation of we don't have the tools, right? As mentioned in the talk before, you will need the PDF interpolation. You would need the integrators. So you would need also the phase space and so on and so forth. The matrix element generator, of course. So this brings us to the situation that we are right now, in that if I want to write some Monte Carlo for a new process, I should only have to worry about the matrix element, about the loops, about the infrared divergences, but this is the only part I'm interested in from the physical point of view. For all the other stuff, I can use tools that already exist, right? I can use a Cuba library that gives me a number of integrators. I can use Rambo for generating the phase space. It might not be the most efficient one, but it will give me a result, and that's all I need to produce some results. If I want to do it in a GPU, even after I've written my matrix element, I'm missing all the other tools. And then I start entering in problems such as you have to copy a lot of things in and out of memory for every event. You need to generate everything on a CPU, so you might be bottlenecked by many other things, etc. So this is the problem we are trying to tackle with VegasFlow and PDFFlow. So basically provide a framework that people can use to start writing their Monte Carlos. So the choice of language and framework, so Python and TensorFlow, has been mainly because from the point of view of the expertise we get from new people coming into the field, they usually know Python. And given that TensorFlow is giving you at the same time CPU and GPU possibilities, and also compatibility with neural network-based integrators, which during the last 2 years there has been a lot of work in that respect. It seems the most logical choice. And there is also the nice feature that is also very easy, made compatible with Bit, CUDA, or C++, or even Fortran, if you wish. And so what is the main idea behind both programs? So basically, it's really easy, air quotes. You just need to batch everything that you can batch. So for instance, in the case of LHCPDF, you don't even really need to change any algorithm. You just need to make sure that the interpolation is done in a batch of points at the same time, so that you ask for an array of X and you get an array of results. You have to change how the algorithm is implemented, but the interpolation algorithm itself hasn't changed at all. And what is the status right now? So right now it's perfectly possible already to write next to leading order calculation using these tools. I don't expect any very complicated calculation to be ready in the next months, obviously, because it can take, I personally know that it can take years before getting any of those running. And therefore we have also focused a lot on being compatible with Fortran, C++, or other languages, so that parts of this framework can already be used with existing codes. Everything is completely open source. It can be found in the organization repository of the N3PDF collaboration and installed with pip and Conda. And And please let us know if there's any difficulties with the documentation or installing the program or using the program, because obviously the more people use it, the more we know about how to improve it. Now to show some quick results. So let me start with LHCPDF and PDFFlow. So as I said before, the interpolation algorithm is exactly the same. So as you would expect, the precision is perfect between both tools. So we are talking numerical precision here. So all tests are done using double precision, be it for the interpolation X for a fixed Q, or for the interpolation in Q for a fixed X. And here in the left, you can see how it improves in GPU over CPU, just because in GPU now calling for more and more points is basically free, as opposed to a CPU. Be this with PDFFlow, which is giving you the multi-threading for free through TensorFlow, or with LHCPDF, where obviously you get a linear deterioration of the performance as you increase the number of points. For actual leading order calculations and next leading order calculations, so we start by porting a single top code that we had for Fortran at leading order. So we ported that to the TensorFlow framework in the most silly possible way. So basically, it's a leading order calculation, so it's not very complicated. So basically, write the same code in Fortran, but with TensorFlow. And then we compare with MATGraph. The reason we choose MATGraph is just because it's very easy to produce any new process, and then you get the multi-threading for free that we would have to have implemented in the old Fortran code. And we see obviously a huge improvement in time to get the same target accuracy. So once we were able to do it with leading order, we tried as well with a next to leading order calculations. For this, we used a vector Boson fusion Higgs production calculation at next to leading order. So it's not very complicated. So it can be, so the diagrams can be dealt by hand. And the same caveats as before applied. We didn't do any specific GPU optimization beyond what was needed to make everything work, obviously, because here you have now subtraction terms and phase space cuts that are very much non-trivial. And compared to the original Fortran implementation, which in this case is well optimized and can run in multiple cores. And even in this case, we see a good improvement when we go from CPU to GPU. And as one might expect, as you increase the memory available in the GPU, so this is the main difference between the RTX and the Titan 5 and V100, the improvement becomes better. One thing maybe worth mentioning, which might seem strange in this plot, is that the two V100 were worse than the Titan 5 because they were sitting in a much worse computer. So you actually got a huge hit on performance due to the fact that basically the parts that are still running in CPU, even if it's just the reduction of the histograms and so on, are very much slower. But all in all, this has a great potential for accelerating the fixed order, higher order calculations. And we did a first implementation with a third-party tool. So this is the Pineapple grid filling tool, which is to be compared with Apple Grid, I guess, which is written in Rust, but it has both Python and C interface, so that it is easily. So we show that it's easily integrable with VegasFlow, even when the Pineapple part is running completely on CPU. So you can, let's say for free again, have this CPU-GPU hybrid model where your calculation is accelerated, and well, whenever it needs to stop to fill the grid, it will. So one last thing to mention is one last thing we implemented was an interface to Dusk to facilitate, because it's not only GPUs and in single machines that one has access to, but to facilitate also the running in a distributed system. Sadly, I don't have any distributed system with GPUs that I can test with, so I don't have any performance plots to show here. So that's all from my side. So I know that there is no need in this environment to convince you, but I hope you still believe that GPU computation can be really useful for the kind of problem that we deal with in the high energy physics phenomenological, at least the phenomenological side of the field, and that is perfectly compatible with competitive with CPU. And I'm very happy. I have to say that I'm very happy about the improvements in the math graph side, because indeed the matrix element is a very much non-trivial part of any calculation. So having the CUDA, a CUDA ready version of most of the matrix elements would be a great boost for this kind of calculation that can take years in CPU hours. And that's everything. So thank you very much.
Yeah, thanks for this nice developments. So any questions or comments? I don't see any raised hands, but one question in the Google Doc from Andrea.
Yeah, hi. Thanks a lot, Juan. This was very, very interesting. My question, you probably answered part of it already. I mean, you mentioned at the beginning that you focused on Python, but that you have some compatibility with C and C++ and CUDA. I was just wondering, do you have some simple examples already made of simple programs which integrate, I mean, where you see the interfaces of simple matrix element calculation or to both PDFFlow and VegasFlow in C++ or C or CUDA? Because for us it would be very interesting, but in Python it would be a bit complicated. Let's say.
Yes, I know. No, yeah. So in the VegasFlow repository, if I'm not remember wrongly, otherwise in PDFFlow, there is an example of a CUDA, of integration with CUDA with C, and in the PDFFlow repository there's an example also with Fortran, which I guess it's useless for this in this context. But anyway, but yes. So we tried to provide all the different examples that we thought were very useful in this case. Obviously, so for CUDA in particular and also C++, is not completely trivial in the sense that you need to know what you are doing. But I would say that so on one hand, we wanted to, one of the reasons we write it in Python is to facilitate access to the community. And I think once you are writing code in CUDA, you know perfectly what you are doing, so you can manage yourself the data transfers and so on. So it's perfectly possible.
Thanks.
Stefano?
Yeah, so when you compare the performances of the various scenarios, you do so with a target accuracy on, I suppose, the total rates.
Yes, so the target accuracy is always, I didn't mention it here, right?
Yeah, it doesn't matter. I mean, my question.
Yeah, it's always on the total cross section. Yes.
Okay, so my question is whether to reach the same accuracy with the standard Vegas and the VegasFlow. If there is any significant difference in the number of points you have to throw. No.
It's actually quite similar. It's more similar in this case than in this case. So for instance, in this case, the integration algorithm under VegasFlow is the same important sampling implemented in Vegas. So from that point of view, the number of points is similar. I'm running double precision, so there's no difference in that regard. However, in this particular case, in the NNLogic side, there's a lot of extra optimization on the phase space side, which I didn't implement it in this example because it was out of the scope, beyond the scope. So you actually needed almost a factor 10 number of points to arrive to the same level of precision. But on the other hand, there's nothing that stops me from implementing this extra layer of optimization on the phase space on GPU. So in principle, if the sampling is the same, the number of points should be equivalent.
Okay, thanks.
Josh, I see you have a comment on the Google Doc question.
Yeah, I guess it's maybe a similar question, except for I wanted maybe a bit more basic understanding on the slide 13, Juan. So can you go through exactly, so I didn't quite follow whether this can be considered as a Vegas versus VegasFlow comparison and not really anything else or at least sort of quantitatively nothing else changed, or whether that's not quite the case.
Well, here there are two things that change. So both three things, because also the matrix element would be written by hand in our implementation, while it's an automatic generation in the case of MATGraph. So rather than nothing changed, it is an example of taking some already made result, in the sense that taking the first thing that comes to mind if one wants result for a specific process, which would be running MATGraph for that process, and the version done in VegasFlow. So where there are changes such as the PDF interpolation, which in MATGraph, I'm going to guess by default would be LHCPDF. I'm not sure. While we are using PDFFlow.
Okay, but it's not really possible to extract the bottom row here, but for the VegasFlow code, if you see what I mean. Like you don't have any feeling for whether if you ran the C++ code on 36 cores, whether it would be drastically different to what you get out of the box from MATGraph or not.
I don't remember out of the blue, but it was way worse. And so if I would add the
right. So I would guess it was worse, not better, right? Yeah.
I mean, it was a old Fortran core, so it was done for a different time.
Okay, I see. Thanks.
Any final questions or comments before we close the meeting? I don't see any raised hands. So thanks a lot for the speakers and for everyone who connected. I think our next software session is on Monday, starting at 4. And yeah, we can close the meeting. Have a nice weekend. Bye.
Bye-bye.
Thanks a lot.
Bye-bye.
Thank
Thanks.
you. Bye.